Hi, my name is Manav, and I'll be presenting my work over the summer at RISS, which is titled Modeling Human Trust in the Commanding of Robot Wingmen. So, this whole thing falls under human-robot collaboration, the basic idea of which is that as complex autonomous systems become more prevalent and integrated into work environments alongside humans, it becomes more important for them to operate in a more socially aware manner. The class of scenarios we'll be dealing with are ones which require the automata to collaborate with the humans towards a common goal. Now, decision making for most complex machine learning models, such as the one warranted for a task like collaboration, are typically very black box-esque, where the inner workings aren't always very obvious. Now, this poses some challenges when considering collaboration. Specifically, evaluating the instantaneous performance of the automata in order to decide the next steps can be very hard, as well as even formulating the next steps, given how the relationship between the control input and behavior is often unclear. Another aspect is that the real world entails imperfections, which can lead to noisy data, which can get propagated into inaccurate information and bad decision making from the automata, which can be quite harmful. All these factors essentially come together to strain the relationship between the human operator and the automata, which causes either undertrusting or overtrusting. Undertrusting causes situations where a human operator will opt to handle tasks which could easily be delegated, which would better be served by being delegated. And overtrusting can cause the operator to overlook inaccuracies and just inadequately monitor the situation. So the question really becomes, how do we account for this? One option, the one we explored, was by having the automata maintain a sense of how much the operator trusts it by modeling the trust. This model can be updated continuously based on the performance of the automata, as well as interpreting the actions made by the human operator. For example, if the human intervenes, it can be interpreted as a loss of trust, and if the human releases control or accepts recommendations, we can gauge that as the trust being relatively high. So there's many different ways to model this, and one consideration is an MDP to represent the automata's understanding of the human's decision making. An MDP is just represented as a tuple containing the set of all finite states, the set of all actions, the reward function, which just dictates the reward for making a particular action to get from one state to the next, the transition function, and gamma, which is the discount factor. Now, the main problem when talking about MDPs is to find the optimal policy, which is what action to take given the state that you're in to maximize the reward function. Here, K is the time step. And given the structure of the reward function and the domain of gamma, it makes sense to interpret the magnitude of gamma as how far ahead into the future the agent in question can see. Now that we've formulated the human trust, we can use inverse reinforcement learning to find the reward function. IRL just deals with finding the reward function under the assumption that the agent is acting optimally, where the agent is the human in this case. From here, the reward function is simply interpreted as the weighted sum of linear features, which we can solve for. Now, the other model is the online probabilistic trust inference model, which essentially treats the level of human-robot trust, T sub k, at time k as a random variable and maintains the belief distribution for trust. This model is represented as the Bayesian network here, generally, and it encodes causal as well as evidential relationships between trust and the factors influencing it. And it also takes into account the evolution of trust over time, like the MDP. As far as methodology, we use these two representations to model human trust with the idea of comparing them. To recap, the former uses MDPs to formalize human trust, on which we performed IRL to learn the reward function for the human in an effort to learn the trust behavior. The latter is to use the Bayesian inference model we talked about. Our experiment involves a two-dimensional simulation of an aerial environment. Here there's going to be one human pilot and 2 unmanned aerial vehicles, as well as 5 targets somewhere on the field. So all targets have a score value of 0, 1, or 2, and these are the opposing targets, and their capability is equal to their score. Now, the human pilot and the UAVs have a capability of 1, and the idea is you'll get this value added to your score if you are successful in the attack. And success is if and only if the attacker's combined score is at least equal to their target. So if the target is level 1, the human pilot could take it on himself. And if it's level 2, like in this case, then it would need to team up with the UAV to take it down. And we scored our experiment on the maximum score that a participant could achieve after 20 trials. At the beginning of the trial, the UAVs will explore to 2 targets, and after that, the UAVs will convey the information regarding the perceived level of or capability of the target with a confidence score. The confidence score we obscure by using Gaussian noise. And after that, the human operator simply chooses to engage one of the 5 targets, and we repeat. After all of this has happened, we also ask the human participant to rate a subjective trust score of how much they trust each of the UAVs. Now, our research goal was to rate the accuracy of the trust rating modeled by the data from the UAVs, with the ground truth being provided by the subjective rating we asked the participants during the experiment. And another thing we did was to compare the 2 different models. And this diagram here is from a Kalman estimation trust model from Lee et al. In 2020. And that's about it. Finally, I'd like to thank all of my RISS mentors. I learned a lot from them, and they made the experience an absolute pleasure. Professor Katya Sakara, Doctors Dana Hughes and Mitsopopoulos, and PhD student Huao Li from UPenn. And of course, co-directors Rachel Birkin and John Dolan, without which RISS would just not be possible. They have put so much effort into it, and it really shows. And NSF for the funding and giving me the opportunity to come here and have this incredible experience. Thank you.